I'm Swizzet, and today we're going to look at n-body collision detection. The demo you just saw is built with React, D3, and MobX. Now, collision detection is something that's pretty simple in theory, but kind of hard to do in practice. In theory, all you need to do on every step of the animation is to first compare every element with every other element, see if they intersect, and if they do intersect, to change their movement vector so that they bounce off. Pretty easy, right? So here's what my first attempt looked like. No good. My second attempt was better. On my third attempt, I added some vector math. The real problem was mass. Balls shouldn't stick together like that. They don't do in real life. So I tried to fix that. No. But in the end, it all worked out. Well, sort of worked out. Mostly worked out. So here's how it works. We're gonna look at the n-body collision part of the problem, and to look into how the rendering part works, check out this video. Okay, first part of the problem is that comparing every item with every item on each step of the animation to check whether they intersect it's kind of slow. It's what is called an O of n times n algorithm, which is really slow. For 5 items, you get 25 comparison of 60 times per second, which isn't too bad. For the 11 marbles that we have, that's already a 11 times 11 is 121 comparisons. Now imagine if we had tens of items or hundreds of items. It's no good. It doesn't work that way. I mean, it works, but it's not going to be very fast, and it's not going to create a good animation experience for the user. We solve that problem by subdividing the space of our marbles into smaller and smaller chunks until we find pairs of marbles, and turn the entire n-body collision problem into a 2-body collision problem. Sort of like this. See, we have 2 marbles and 2 marbles here, and these are our collision candidates. They're close enough to potentially be colliding, so we only have to check these 2, and then we know if they react to whatever. But basically, each marble can only collide with its nearest neighbor, which means that we only have to compare each marble with one other marble. The easiest way to do those subdivisions of our space is by using a D3 quad tree. Basically, the way it works is we use this quad tree data structure where we feed it all of our data points or all of our marble positions, and it creates a subdivided space for us where we can say, hey, what is the closest marble to our current position or to any position? This is what the code looks like. We have a function called moveMarble that we use to iterate over all of the marbles on our animation. And then for each marble, we create a new quad tree with an extent that goes around our entire picture, and then an x and y accessor that tells the quad tree which attribute to look at for every marble and get its position. And then we add all marbles except for the one that we're currently moving. The reason we don't want it is because it would always be the one that's closest to the current marble. Does that make sense? I think it makes sense. And then to get a collision candidate, we look for any marble that's within 2 marble radiuses away from the specific marble that we're looking at right now. See, if we have 2 marbles, this is the one we're currently looking at, which at X and Y, and then if the center of the other marble is within 2 radiuses, then that means they're colliding. If it's further away than 2 radiuses of marbles, then they're not colliding. And yes, we are relying on the idea that all marbles are the same size, because that makes our life a lot easier. Now here's how deflecting marbles in a collision goes. Imagine we have 2 marbles, they've just collided. Each has its own vector of travel, that's the direction it's moving in. And then the first thing we need is a collision vector between them, which tells us which direction they collide in. We do that by imagining vectors that go from 0 to each centers. They're called D, D1 and D2. And then to calculate the direction of their collision, we calculate D equals D1 minus D2. After we have that, we need a magnitude of that vector, which we calculate by dividing it by its size, and we get the size using the Euclidean formula, which is square of each position multiplied with itself, squared, each position squared. And then once we have that, we can calculate the delta velocity vector, which is just velocity 1 minus velocity 2 times the directional unit vector for the collision. And then we just apply that vector to each velocity. And this looks kind of weird in mathematics like this, so I'm going to show you the code. So here's what that looks like in code. We first get the vector for the collision candidate, or rather its position. Then we calculate the distance vector between the 2 center points of the marbles. We use the Euclidean formula to get the magnitude of that distance. And then we kind of do everything else in one step. We calculate the dot product of the current movement vector of our marble with the distance vector, and we normalize it to turn it into a unit direction vector. Normalizing means dividing it by its magnitude. And then we apply that unit vector to the current direction of the marble that we're looking at. Now, the tricky part here is that even though we're looking at just this particular marble and calculating its vector, we also make the same change for the candidate, so for the other part of the collision, just in reverse. The reason we do this is so that both marbles can share mass in a collision. So it's not like this is traveling like this and the one bounces off, but they're traveling like this and then they both bounce off each other. And then at the very bottom of our simulation step function, we have a loop that goes through all of our marbles and applies the move marble function, gets each marble's new position in vector and applies it to the marble. Now, yes, we are applying that stuff to not current marble straight in the loop or straight in the iterator, so we don't really have to return it, but honestly I don't know why I did it this way. I just did. It's completely unnecessary. And the reason is that it's unnecessary is because our marbles are actually MobX observables. If you look at the top of the physics file, you'll see that physics is actually a MobX store and marbles are an observable array. That means that whenever we change properties of one of the marbles, they immediately get propagated through the MobX engine and they re-render each marble. A marble component of what's being rendered is an observer of physics, so it just re-renders with new positions, and that's what drives the entire animation. We go in a loop, we change properties in the observable array of marbles, and then the marble renderer component, which is an observer, automatically re-renders and our marbles move around the page. You should read the article for more details and subscribe to this channel because I'm going to be making more cool videos like this.